Welcome back everyone. In the last lecture we had seen what is root locus of a system. Root locus are the collection of all those points which are closed loop pole locations of the system when typically the value of k is changed from 0 to infinity. Today we try to learn a few of the basic rules of drawing root locus. Understand this, that now given the softwares that we have, we can always draw root locus just by typing one line of code. However, still we need to know these rules, the reason being that in order to analyze the root locus that you get using these softwares, you should understand the root locus first. You should know how to read the root locus. If you do not even understand how to read the root locus, looking at the plots you will not be able to make out anything. So that is the reason we need to learn these methods. It is not to draw it on a pen or a paper, because now we have softwares. We do not need to draw these things. We can easily plot these things using softwares now, or writing a simple code also. You can write a C code for this and you can plot this. However, we should know what are the rules, because this will give us insight into the root locus, and during controller design also you will see it will help you. Okay. So let us go ahead and look at the rules to draw, the basic rules. At least today we will learn the basic rules to draw root locus of a system. So root locus, as I had already told, starts from as k is varied from 0 to infinity. So the starting point of a root locus is k equal to 0. So at k equal to 0, what are the closed loop poles of the system? And the end point is k infinity. At k tending to infinity, what are the closed loop poles of the system? These are trivial, it looks trivial, but it at least gives you the starting and the end points of the root locus. So let us try to do that, and side by side as we go through the rules, we will also go through an example and try to implement the rules that we are seeing, and at the end we will reach to the root locus of that system. Now again, another important thing which students gets confused about, we are drawing the root locus for the closed loop system using the information of g and h here. K is getting varied from 0 to infinity. I am using the information of g and h, and remember that this is the equation that we solve to find out the closed loop pole locations, and this was equivalent to two criteria. One was the magnitude criteria and one was the angle criteria. So the points which satisfies the angle criteria are the closed loop poles, and then we check the magnitude criteria to find out the value of k. This is what we had discussed in the last class. Okay. So you can see that this quantity here is one of the most important quantities, because this gives you an information about what qualifies as your closed loop poles. So therefore this g into h term, okay, is known as the open loop transfer function of the system. Okay. Why is it called open loop transfer function? Because if you open this loop, the transfer function of this system becomes g into h. I am removing k from this because k we are varying. In this root locus example, I am varying k, but if you knew k already, then the open loop transfer function would be k multiplied by g into h, if you knew k already. But since in this case we are varying the value of k, we do not know what the exact value of k we want for a particular location, so we will not take k into consideration. So g into h in this case is the open loop transfer function of the system. So from now on I will call it open loop transfer function. So we have three names now. One is plant transfer function, which is gh, okay, and then the other is the closed loop transfer function, which is the transfer function of this entire system, okay, and then another is open loop transfer function, which is you open this loop and then you have g into h. So open loop transfer function is g into h. Okay, remember that. Let us start at the starting point. What are the closed loop pole locations at k equal to 0? Now at k equal to 0, see, g is a transfer function, so that will be a numerator and the denominator, h will have a numerator and the denominator. So in that case 1 plus k gh equal to 0 will be something like this, and this is nothing but I multiply both sides by dg into dh. So this is what I get, but k equal to 0, so we will get dg into dh equal to 0. So what are the points which are the starting points, the roots of dg and dh multiplied. What is dg into dh? dg is the denominator of g and h is the denominator, gh is the denominator of h. So, these are the open loop poles of the system. So, the poles of g into h, I will not mention s again, okay. Just remember that I am talking in Laplace domain, because each and every time telling s, you can see that how many times I have stumbled while telling gh into hs. It is almost a tongue twister, right. So, let me just call it g into h, okay, gh. So, the poles of gh are the starting points of the system, because dg into dh equal to 0 are nothing but the points which satisfies this are nothing but the poles of g into h. So, the poles of the open loop transfer function, open loop poles, the root locus starts at the open loop poles of the system, okay, and the corresponding gain at that point is k equal to 0, because that is the starting point, okay. So, in this case you see what is the starting point, then h is 1 in this case. So, gh is s plus 5 by s into s plus 4. So, where are the open loop poles? The open loop poles are at 0 and minus 4, right. These are the open loop poles of the system. Let us go for k tending to infinity. This is the end point, okay. So, basically we are trying to see where we are starting and where we are ending. So, we are starting at the open loop poles and where we will end at k tending to infinity. So, at k tending to infinity, again if we go ahead and write down the equation, this is what we will get. Instead of k, now I am writing 1 by p, because k tending to infinity means p tends to 0, right. So, I can rewrite this equation, this is what we will get, and now since p is 0, we are left with this part only, which is ng into nh equal to 0, which means that the end points will be the zeros of g into h. So, the root locus ends at the open loop zeros of the system. So, if you take g into h, this will be a transfer function numerator by denominator, right. The roots of the numerator will be called the open loop zeros of the system, and the roots of the denominator will be called the open loop poles of the system. Reason being, gh we defined as open loop transfer function, okay. And what will be the value of k at the end point? The value of k will be infinity. Now, in this case, you try to find out the end point. In this case, you can see that the end point will be minus 5, right. So, the end point will be minus 5, because the open loop 0 in this case is minus 5 only. So, I have drawn the starting points minus 4 and 0. These were the starting points of this system, the open loop poles of the system, and the open loop 0 of the system is minus 5. Now, you see the next rule is how many number of branches will the root locus have, okay. Now, you see if there are 2 starting points, then there will be 2 branches, okay. Since there are 2 starting points, there are 2 branches. So, the number of branches will be equal to number of open loop poles of the system, okay. Now, you see we are drawing root locus, right. If there are 2 branches, if 2 branches are starting from some point, then these 2 branches will end somewhere, but we have only found out one end point. Where is the other end point? The other end point will be at infinity, okay. I will come to that again soon. Rule number 3. The rule number 3 is that the root locus will be symmetric about the real axis. Why will root locus be symmetric about the real axis? What is root locus? Root locus is the plot of the closed loop poles, right. Now, suppose there is a closed loop pole at this location. So, this is a plus jb. Won't there be a closed loop pole at a minus jb also? Because the characteristic polynomial that we are dealing with, that is 1 plus k g h equal to 0, you will get a polynomial, right. That polynomial will be equal to 0, and the coefficients of that polynomial, this is a polynomial in S, the coefficients of this polynomial will be real numbers. If the coefficients of these polynomials are real numbers, then if a plus jb is a root of that polynomial, then a minus jb must also be a root of the polynomial, which means that if a plus jb is a point on the root locus, suppose this is a closed loop pole, then a minus jb also must be a closed loop pole. If c plus jd is a closed loop pole, then c minus jd is also a closed loop pole. In this way, if all these points are closed loop poles, then at each and every point there has to be a complex conjugate. So, there must be symmetry in the root locus about the real axis, okay. Next is, where does the root locus lie on the real axis? So, on the real axis itself, directly on what is the real axis? This is the real axis. On this real axis, where does the root locus lie? Here is the rule. If the total numbers of poles and zeros on the real axis to the right of a point on the real axis is odd, then the point lies on the root locus. I will explain what does this mean. Suppose I ask you this question, can this point become a closed loop pole? So, when I ask you this question, what should you think? For a point to become a closed loop pole, what are the conditions that it has to satisfy? It has to satisfy 1 plus kgh equal to 0, right. In other words, this is also equivalent to satisfying the magnitude criteria and the angle criteria, right. These are the two criteria that has to be satisfied. This is if and only if thing, like it is equivalent. Instead of solving this equation, you can go ahead and check whether it satisfies angle criteria and magnitude criteria. In the last class itself, I have said that the angle criteria is the most important one, because angle criteria is not satisfied, even if you get the value of k, it does not make sense. It will not help you, okay, because the value of k can be found out at any point on the complex plane, but the angle criteria is not satisfied by every point. So, now what I will do is I will check whether angle criteria is satisfied at this point. So, we know how to check angle criteria. For this example, these are the pole locations. So, I am trying to check whether the angle criteria is satisfied. So, if I have to check whether the angle criteria is satisfied, what do I have to do? So, again remember, angle criteria says that angle of GH must be equal to odd multiple of 180 degree. So, I am checking GH here. So, G into H is G itself. So, now you have to draw a phasor from here to here. What is the angle? 0. What is the angle from here to here? Again 0. What is the angle from here to here? 0. So, there is no way that the angle criteria is getting satisfied by this point. However, what about this point? At this point, if you draw a phasor, then this will contribute to 180 degree, whereas the phasors from these two will contribute to 0. So, in this case, any point that lies in between these 2 points will satisfy the angle criteria. Will the angle criteria be satisfied by any point here? No, because you see, if you take any point here, the phasor from here will give you 180 degree, the phasor from here will also give you 180 degree, they will add up to give you 0 degree, right. So, the angle criteria will not be satisfied for any point here, whereas the angle criteria will be satisfied for this part again, because there will be 3 times of 180 degree. In other words, what we mean is that if you take a point and to your right there are odd number of poles and zeros, then that point must lie on the root locus. So, in this case, this entire thing will lie on the root locus, and this entire line till minus infinity will lie on the root locus. Okay, I hope I could make myself clear. So, in this case, you see the root locus must lie from minus infinity to minus 5 and minus 4 to 0. This I am only talking about the real axis. It can go outside also, okay, but this entire line must be on the root locus. This entire line must be on the root locus, okay. This brings us to the 5th rule. Remember, I said that, okay, now see what are the informations that we have. We know that this entire line lies on the root locus and this entire line lies on the root locus, and we know that the starting points are this. So, they will start like this, from this side also they will start like this, right, because it cannot go in this direction, okay. Can it go in this direction? If it goes in this direction, then one branch must come out in this direction also, right, because they have to move symmetrically, right. They must be symmetric about the real axis, but there is only one pole here. So, only one branch can come out of a pole. Where will the other branch come out? There is only one starting point at that point. So, there is no way that this can come out in this way. Can it go in other directions? It cannot go in these directions also. The same logic. If 2 branches have to come out, there has to be 2 starting points here, but there is only one starting point here. So, only one branch can come out. So, the only way it can come out is it comes out through the real axis. In the same way in this case also. So, that means there will be one branch coming this side, one branch will be coming this side, and they will collide somewhere in between, okay. Then what will happen? Now, you see one of these branches must terminate at minus 5, because minus 5 is an end point, right. One of these branches must go and terminate at minus 5. Suppose it went something like this and went to minus 5. Then the other branch also will symmetrically go like this. Now, I cannot draw a symmetry of this. So, symmetrically it has to go out like this, and then can it go to minus 5 again? No, because 2 branches cannot move towards the same point, okay. They cannot overlap, they can overlap only at one point, and then they have to go away from each other. Now, in this case, so if one of the branches goes to minus 5, where will the other go? The other has to go in this direction, because first of all, we know that this entire from minus infinity to minus 5, this entire line lies on the root locus. So, the other branch must go towards minus infinity. So, that is what I am saying. So, if you know what were the total number of branches, the total number of branches were 2 in this example, and we get only one end point. So, where will be one of the branches will terminate at that end point, but where will be the other branch going? The other branch will go to minus infinity, okay. Now, the question is, how will it go to infinity? See, this infinity thing, there are a lot of infinities, right? This, you can go to infinity from this direction, this is also infinity, this is also infinity, this is also infinity. Infinity, there are lots of directions of infinity. Infinity, like in all directions there are infinity, right? So, how will it go to infinity? Okay. Now, it turns out that root locus approaches infinity with the help of asymptotes. Asymptotes means you will have some lines and it will go to infinity being parallel to this line, and at t tending to infinity it meets that line. Okay, that is what asymptotes are. So, in this case, how many number of asymptotes we will have? Because we have two branches that will start, one of them will end at -5, the other must go to infinity. So, there is only one line that will go to infinity. So, the number of asymptotes will be the number of open loop poles by minus the number of open loop zeros. Okay, fine. So, in this case the number of asymptotes is 1, because that we have just now argued, right. One of the branches will go to infinity, that means there is the number of asymptotes in this case is 1. Now, asymptotes you have to draw at some point, somewhere you have to draw the asymptote line. So, which point to draw that line, at what angle to draw that line is called the point is called the centroid, and the angle is called the angle of asymptotes. So, we will find that out now. So, the intersection point of the asymptotes on the real axis is called the centroid, and the formula to find that out is sum of real parts of the open loop poles minus sum of real parts of the open loop zeros divided by the number of open loop poles minus number of open loop zeros. I am not going to do the proof of this, okay. You can find it in the Norman-Nice book, it is there, the proof is there, you can go ahead and read that. I will directly use the formula. So, what it says, sum of real parts of the open loop poles. First of all, what is the open loop transfer function here? The open loop transfer function is s plus 5 by s plus 4, s into s plus 4. So, sum of real parts of the open loop poles. So, open loop poles in this case are -4 and 0, sum of those, and then minus sum of real parts of the open loop zeros, the open loop 0 is -5, right. Then divided by the number of poles and zeros. So, this is what it is. So, these are the open loop poles, this is the open loop 0, and then divided by 2 minus 1. So, the asymptote will be at 1. So, at this point we will have the centroid, but at this point if it is a centroid we have to draw one line. Remember, how many asymptotes do we have? We have only one asymptote, because there is only one line that will go to infinity. And how will the root locus branch go to infinity? Being parallel to this asymptote line, and it will reach this asymptote line at t tending to infinity. That is the idea of asymptote. So, angle with the real axis of the asymptote is given by 2k plus 1 into 180 degree by p minus j, where k are plus minus 1 plus minus 2 whatever values, integer values basically. And in this case we will get only one angle of asymptote, because we had only one asymptote. So, only one value we will get. So, let us try to calculate this. So, 2k plus 1 into 180 degree by 2 minus 1, because p here is the number of poles, z here is the number of zeros. So, p is 2 minus 0 of the open loop pole, of course, open loop transfer function, and this comes out to be 2k plus 1 into 180 degree. Now, you put the value of k, see, put the value of k equal to 0, you get plus minus 180 degree. This is the same line, right. If you put k equal to 1, you get 3 into 1 plus minus 180 degree. This also is the same line. Plus 180 degree also is this line, minus 180 degree is also this line, 3 times of 180 degree is also this line. So, see, all the points are leading to the same angle. That is what will happen, it will repeat. So, you do not have to check for each and every value. Since you need one asymptote, just check for one value and that is fine. Say k equal to 0 I am checking, and it comes out to be 180 degree. You can take plus 180 degree, minus 180 degree, at the end of the day both are the same directions only, right. So, basically what you will do is, from this plus 1 line you will, so we got alpha equal to 180 degree, from the plus 1 line you draw this asymptote line. So, the branch will be parallel to this line, or in this case it will overlap this line itself. And finally, we have the last basic rule. There are more rules, but the last basic rule, which is the breakaway point or breakin point. What is breakaway point and breakin point? See, we had already drawn this basic diagram, right. We know that the root locus will start like this, and from this point the root locus will go in this direction, it cannot go in other directions, and then it will come and stop at one point. At this point there will be multiple poles, right. There are two poles. Again, what are root locus? Again, I am just capping things. What are root locus? Root locus, suppose I say this point is a closed loop pole. Now, if this is a closed loop, because this satisfies the angle criteria, right, the rules that we are using are only angle criteria. So, this point is a closed loop pole. If this is a closed loop pole, then we must have a value of k at which this is satisfied, because I can use, it satisfies the angle criteria. Now, I can use the magnitude criteria to find out the value of k. So, what are the locations? So, these are what? At k equal to 0 I am at this point, okay. At k equal to say 1 I am at this point, and this one will be at this point. What is the meaning of that? So, when I put k equal to 1 here, the closed loop pole locations will be this and this. When I put k equal to 2 here, the closed loop pole location will be this and this, say. So, in this way, as the values of k are increased from 0 to infinity, as I increase the value of k from 0 to infinity, the closed loop poles are changing. Now, at a particular value of k, both the closed loop poles will be at the same point. That point where is called the breakaway point, because from that point it cannot go, it cannot cross each other out, because then we will be repeating the same closed loop poles again. It will go out of this real line now, okay, and it will go out of this real line, and then it will come back, and then it will come back like this, and then in a symmetric way, of course, and then one branch will go in this direction and the other branch will go in this direction. Of course, you can ask why not like this stops here and the other branch comes here. See, the symmetry is lost, okay. You can always ask me this question, why not like this? If I go like this, if I come like this at this point, why doesn't it just come here and the other branch also comes here symmetrically, and then one branch only moves in this direction? Is it possible? Think about it. If as I increase the value of k, it comes to this point, okay, and it ends at this point suppose k was 100. So, this branch also at this point k is 100. Now, at k equal to 101, will one of the poles, one of the closed loop poles be always stationary at that point? Only one pole will change. That will never happen, right? Think about from a polynomial perspective. If the value of k is changing, both the pole locations will change, right? Is it that one location will remain at one point and the other location will be changing? That is not going to happen. So, this is not possible their way. That is why both the branches will keep moving, okay. So, this point, so this point where there are multiple poles, this is called breakaway point, because at this point the branches will break away from each other, and then they will come back and again meet at a point. This point is a break-in point, because both these branches are breaking in to this point. So, this point is called a break-in point, and from break-in point one branch will go this direction and the other branch will go that direction. This intuition will develop as you practice more and more root locus problems. Of course, this is the first problem that you are seeing, so the intuition might not be there yet, but soon you will see that this intuition will be developed if you practice more and more problems. Now, the question is, how do I find out these points? Okay. Now, in order to find out these points, you have to solve this equation dk ds equal to 0. Okay. Again, the proof of this is there in the books, so you just go ahead and search the textbooks, you will get it. So we will have to solve dk ds equal to 0. What do you mean by dk ds equal to 0? So, I had 1 plus k gh equal to 0, right? From here I will write k equal to minus 1 by gh, and then I will find out dk ds and make it equal to 0. The points at which this equation is satisfied will be the breakaway and break-in points. So, let us see what does that mean. See, so what is dk ds equal to 0 means? Let me just write down. So, 1 plus k gh equal to 0. This is equal to k equal to minus 1 by gh, and this is nothing but ds by ns, right. If I say that g into h is nothing but numerator by denominator, so this is nothing but this. So, now if you do dk ds equal to 0, what do we get? This implies ns whole square d dash s ns minus n dash s ds equal to 0. But this is equivalent to saying that d dash s ns minus n dash s ds equal to 0. So, solving dk ds equal to 0 is equivalent to solving this equation, and that is what we are going to do. Okay. So, finding out the breakaway break-in point is equivalent to solving this equation. See, I will solve this equation for this example. In this example, ns is s square plus 4s and ds is s plus 5. So, if you find out ds ns minus n dash d dash ns minus n dash ds, okay, then this is the expressions that we will get, and we have two roots. These are the two roots. And where are these two roots? These are the two root locations, right. So, these were the two roots, these are the two root locations, and you see that means this will become your breakaway point and this will become your break-in point. Now, when these branches will break away, can they go like this? Yes, they can go like this also, but the breakaway point will be always this angle at which they break away, the angle at which they break away will be 180 degree by r. Now, at this point there are two branches coming in. So, r is 2 in this case, okay. That means, there are r number of poles, closed loop poles that are departing or breaking in. So, at 90 degree, 180 degree by 2 is 90 degree. So, at 90 degree one will go up, at minus 90 degree the other will come down, and then they will move in this direction. Here again, since two branches are coming in, they will come in at an angle of plus 90 degree, and then this one will come in at an angle of minus 90 degree. Okay. Let me draw the root locus now. Okay. So, now we know everything. We know that this branch will go in this direction, okay, and say that this is the branch which will break away from this point at 90 degree. This comes out and comes inside this, okay, this is what it will be. And the other branch, let me see if I can get a different color, maybe a blue color. The other branch is coming like this, okay, this will go like this, and then this will come like this. Now, one of these branches will go to this direction. Which branch we do not know, I mean, because that we cannot differentiate. Okay. So, one of the branches goes this direction, and the other branch will go in this direction. Yeah, the diagram should have been like this, should be on the real line, and let me just redraw it. This is what it is, and the other line would be. So, this will be the root locus of this system. We will end at this point today, but we will take another example and see the other rules also, and I will revisit this example again. Okay. Thank you.